Well, I'll ask first, do you have any questions?
Yes. Question 8.
Question 8. Good. Get my iPad open. All right, question number 8, Ocho. Question. All right, so we have the sum. K equals 1 to infinity. We have 1 plus a over k. And this is all raised to the 12k power. Okay. All right, so remember the definition of E? E is the limit as n goes to infinity of 1 plus 1 over n to the nth power. And this works out to approximately 2.718. Remember that? That's infinitely many decimals. Doesn't this kind of have the form of E?
Yeah.
Yes, it has that form, doesn't it? So what I suspect then is that the limit of this expression as k goes to infinity is not going to be 0. And the divergence test says that if the limit of this expression is not 0, the series diverges, right? So if the limit, that's what I'm going to do. I'm going to find the limit of this expression as k goes to infinity and see if I can show that that's not 0 and then this series therefore diverges. Does that make sense? So this is what prompted me to do that. So you need to be familiar with this. Because otherwise, if you're not familiar with this and you look at that, well, you might think the limit would be 1 because as k goes to infinity, this goes to 0. So you might think the limit would be 1, which means it would diverge. But that would, while that would answer the problem correctly, that would be the incorrect means to get to that answer. Does that make sense? So I'm going to do it in terms of x. I'm going to do the limit as x goes to infinity of 1 plus a over x, all raised to the 12x power. All right, to do this limit, we have that problem where we have a variable in the exponent position. The only way to get that variable down is with logarithms, correct? That's our only algebra tool to do that. I mean, we could use the root test and cancel that variable. Let's do this and I'll show you what happens if we try the root test, all right? So to get that down, we're going to have to use logarithms. So we're going to let y equal this limit. And then we're going to take the natural log of each side. And I'm going to put the natural log inside the limit. We can put it in or out. Like that. And then I'm going to use that property of logarithms that allows us to bring this exponent down. Now, as x goes to infinity, the argument inside this logarithm is going to go to 1, correct? Because that term will go to 0, and natural log of 1 is 0. So this logarithm is approaching 0. If we move this 12x, write it as 1 over 12x below, now we have an expression that is in the form, or a limit that is in the form 0 over 0. And because as x goes to infinity, 1 over 12x, that goes to 0. And the inside of the natural log goes to 1, and natural log of 1 is 0. So we have 0 over 0 here. So if it's either infinity over infinity or 0 over 0, we can use L'Hopital's rule, right? So let's use L'Hopital's rule. The derivative of natural log is 1 over the argument, so that's going to be 1 over 1 plus a over x. And we have to apply the chain rule, so it's times the derivative of the inside. The derivative of 1 is 0. Scratch paper work over here. The derivative of a over x, well, that's like ax to the negative 1. Bring the negative 1 down, and you got negative ax to the negative 2, which is negative a over x squared. So the derivative, chain rule here, the derivative of the inside is negative a over x squared. So times negative a over x squared over, now the derivative of this denominator, 1 over 12x, scratch paper work again. 1 over 12x is like 1/12x to the negative 1. Bring the negative 1 down, subtract 1, we get negative 1/12x to the negative 2, which is negative 1 over 12x squared. So that's the derivative of our denominator. You know, maybe this is correct, but maybe it would be more clear if I wrote this like just so negative a over x squared like that. Okay? So it looks more like it's on the same level. Might be a little more clear. Now, to divide these, we multiply by the reciprocal. So if you imagine a negative 12x squared over 1, negative divided by negative is going to be positive. The x squareds are going to cancel out, correct? Everybody see that? X squareds canceling out. And we're going to end up with a over 12. No, I'm sorry. We're going to end up with 12a, right? Scratch paper work. I'm getting some blank stares. Times the reciprocal. The x squareds cancel out. Negative times negative is positive, 12a. So those two reduce to 12a. And it's going to be on top, the numerator. Okay. Now, x is going to infinity, so a over x is going to 0. So all we have in the denominator here is 1. A is a constant relative to the limit, so this equals 12a. But remember, natural log y equals 12a. The limit is equal, that we originally needed is y. So we need to solve that for y. The base for natural log is e, so this means that e raised to the 12a power equals y. So that means this limit is equal to e to the 12a. All right? So maybe we should just rewrite that to be very clear. So to make it really clear, the limit as x goes to infinity of 1 plus a over k raised to the 12k power equals 12, I'm sorry, e to the 12k. Is there any value of a that could possibly, any real number value of a that could make this equal 0? E raised to a power, even if it's e to the 0, it's not equal to 0, right? E to the 0 is 1. So there's nothing that would make that 0, is there? And this is not equal to 0. What does the divergence test tell us if that limit is not 0? Diverges by the divergence test. All right, let's see what options they gave us in Pearson. The limit of the terms of the series is blank, so the series diverges, but there it is, D. The limit of the terms of the series is e to the 12a. So the series diverges by the divergence test. Notice it told us up here, a is real. So crazy stuff could happen if a was allowed to be complex on a form of I, the square root of -1. Crazy things can happen. I don't know if it can make it 0, but crazy things could happen. And we're going to see that in this chapter 11. I can't wait to show you. Fantastic. Did that help? All right. That was actually one I noted here that we needed to look at. Do you have some other questions or any other questions about this problem, about how we did that limit? You all okay with that? Yes? 5? Yes. Identify a convergence test for the following series. So all that first sentence says is to identify the test. It doesn't say to do it. If necessary, explain how to simplify or rewrite the series before applying the convergence test. You do not need to carry out the convergence test. All right, anytime we see two terms being subtracted, like this, I know this one has inverse tangent, so that wasn't what we commonly saw. We want to check for the telescoping series. Let me do a similar question. There we go. You want to check for the telescoping series, so let's just look at what would happen here. It says we don't have to carry it out, but I just want you to see it, to review it. Okay, so if we start putting in numbers for K, we're gonna get inverse tangent of 25 minus inverse tangent of, we're putting in 1 for K, that'd be 25 minus 25, which is 0. So that's what happens when we put in 1. Now if we put in 2, we're gonna get inverse tangent of 50 minus inverse tangent, that'd be 50 minus 25, which is 25. And you see that this one and this one will cancel out, correct? Positive inverse tangent 25, negative inverse tangent 25. So if we continue this, pairs are gonna just keep on canceling out. Let's put another one up here. If we put in 3 for K, we'll get inverse tangent 75 minus inverse tangent 25 times 3 is 75, minus 25 is 50. So we see that that inverse tangent 50, the negative one over there, will cancel out with this inverse tangent 50. Every time we add one, another pair is going to cancel, another pair is going to cancel. And pretty soon there's only going to be 1 or 2 terms left over here. Everything's going to cancel in the middle, and then we'll have something in the end in terms of n, right? And everything will whack out. We don't have to carry out the test. It just says here the series can be tested for convergence using, okay, the answer is going to be the telescoping series, but limit comparison test, you would have to come up with a series you have knowledge of to compare with that. And it has to be something that behaves similarly. We don't have any, do we? No. Divergence test, well, as K goes to infinity, that's going to go to 0 actually, and the divergence test will be inconclusive. Not a p-series, so that doesn't apply. It's not geometric, that does not apply. Alternating, well, there are some alternating signs going on in there, but it's really not an alternating series. Each term has the same signs. Does that make sense? Ratio test, that's not going to apply here. All right? So, properties of a telescoping series, and that's all we have to do. Did that help you? Oh. I was reading all that thinking you were looking at what I was saying. Yeah. So I'll just do a similar one. Okay, this would be the same thing, just change the numbers. I was looking through all these when I was talking. And property of telescoping series. Okay? Oh, you still couldn't see it, could you?
No.
Okay. Okay. Limit comparison again, you'd have to have a series that you have knowledge of to compare it with. We don't have anything for inverse
But
tangent.
usually given, right? Like,
What's that?
For that, like if it was a limit comparison, then there's a given series that you compare to, right? Or do you have to
There
do-
doesn't have to be.
Oh, not always.
No, you might have to come up with it yourself.
Okay.
When you see this, when you see 2 terms subtracted, it's not guaranteed to be telescoping, but highly likely. All right? 2 terms subtracted, check telescoping. That should prompt you to check it. It's not guaranteed, but check it. All right, others?
11?
11.